Okay, so because of unfortunate circumstances, Code Forces is currently down. So um yeah, there's nothing I can really do about that. It was down for like the past like 2-ish hours. So yeah, um there's not much we can do about that besides like wait for it to get back up. So currently the prompts for today aren't posted yet, but we can still get into our lecture because first we're not going to be talking about the problems for a long time. Yeah. Um, yeah. Um, I guess we can start now. Uh, actually, okay. So yeah, the problems from last time. So the problems from last time were pretty complicated. It seems not a lot of people were able to make too much progress on them. So I guess for anyone who has solved A, does anyone want to share their solution? Does anyone um does anyone want to okay, Zach, do you want to share your solution?
Okay, so basically what I did was like first of all you have A1 and then you want to loop through the digits to find which one is the smallest and
Mm-hmm.
the biggest. And you do that by like repeatedly dividing by 10 and
Mm-hmm.
also like finding the remainder when the number is divided by 10. And you just keep doing that and then you find the min and the max. And then you update whichever A, like A1 or A2 that you're working with. And then you just keep going until you get
Mm-hmm.
to AK, but like sometimes AK is too large. And what
Mm-hmm.
I noticed was that if either the minimum or the maximum is 0, then the number all of the AKs after a certain point they're just the same. So like you can once you get to a 0, if you have a 0 in your number, then in one of the AKs, then that means that you're done and you can just print that number. And yeah, that's my solution.
Yeah, that's very good. So I tried to draw this on my trackpad, but yeah, this is basically the solution. So in each operation, you just find all the digits and keep simulating the process. But you also notice that once a 0 digit appears, you're basically done because it'll never change again. So um, yeah, um, yeah. Does anyone have any questions about that? Okay, so yeah, here's my code for this problem. As you can see, it's pretty simple. Yeah, uh, yeah. So for problem B, does anyone else other than Zach preferably have a solution to this problem that they would like to share? Oh, Sean, do you want to share your solution?
Yeah. So I made a for loop, and then it goes to t, and then I made a counter inside that for loop so that every time, like every single test case, the
Mhm,
counter will set back to 0. And
mhm,
then I made a while loop that tests if a to the like ai, like a to the array index I, if it's
mhm.
less than or equal to ni, and I is less than equal to ni, then like you keep running
Okay,
until
wait,
that.
Sean. Try to like explain the idea of your solution and not like the actual code itself, if you know what I mean. Like,
Okay then. So I guess I basically did like if like the like if like the digit, like the number, if like it's less than or equal to the number that you're trying to get like more than,
mhm,
then like it'll repeat,
mhm,
and it'll keep alternating between the smallest number and the biggest number, like adding.
mhm.
So like first you would do the smallest added to the biggest, and then that would become the biggest, and then you would do the other one, like set the other one to become the biggest, so that it does it in the smallest number, and then you would print out like your like, and then you would have a counter, and like you would add it every time you do an operation, and then you print out that counter once it becomes, one of them becomes greater than ni,
Yeah,
like the
okay.
number you're aiming for.
Yeah, yeah, that's correct. So the idea is basically that whenever you're doing an operation, the maximum number is changing. So you can basically just keep alternating which one you do. And then at some point, it'll be bigger than n. And once that happens, you just return. So yeah, um, yeah, that's correct. So yeah, here's my code for it. It's also pretty simple. Yeah. So the third problem, I think not a lot of people solve this problem. So for the few of you that did, would you be willing to share your solution, or should I uh, explain the answer to this problem? Okay, so it seems no one who solved the problem wants to explain their solution. So that's fine. I'll explain essentially what my solution does. So my solution is essentially where you basically like you notice that all of the numbers are less than or equal to 1024, which means that when you take an XOR that of any k that is greater than or equal to 1024, the term of 1024 will never cancel. And that means that in the new array, it will never be equal to the old array. So we can always just like discard that. So that means that all of the k that we have to consider is less than 1024. So now that we know that all of that is less than 1024, we just need a way to efficiently check whether that works. So the way we efficiently check whether it works is we can just go through each element and then create a new array that is basically that element XORed with k. And what that does is if you have the old array and the new array and you have and you want to check whether they're the same, what you can do is you have two ways to do that. You can either sort both arrays and then check each element individually, or you can have another array which is counting the number of each. And when you're counting the number of each, then you can basically check whether the counts are the same. So in my code, I'm using the counting version. So here it's a bit more complicated to do the counting version, but the counting version is also faster by a factor of log n. So yeah. Does that make sense to everyone? Okay, so if there aren't any questions about this problem, then we can move on to the next one, I guess. Okay, so our first topic, we're going to be talking about two topics today. Our first topic that we'll talk about today is sorting and searching and some of the things you can do with sorting and searching. Sorting and searching is a very common topic within both bronze and silver, and in many cases, like sorting will be very useful for various problems. But first, how do you even sort? Well, sorting algorithms can be very complicated, but you will not need to understand them. In many cases, you literally just need to be able to know how to call the function. So in C++, you can sort an array using sort array and array plus n. This format is actually very complicated. You can do a lot of interesting things with it, but it's very complicated if you don't understand what it's doing. So the first parameter is basically the start index. So array or array plus 0, both of them work. And the last parameter is the n that you want to sort. So array plus n, or yeah. And what this will do is it'll sort all of the elements from array 0 to array n minus 1. So if you wanted to sort all of the elements from array of 1 to array of n, then you need to do sort array plus 1, array plus n plus 1, which is a bit complicated, but it allows you to do some interesting things. In Java, it's much easier. All you need to do is call arrays.sort array. However, there's a lot of interesting things to do with this because in C++, you have to include a special package, which is include algorithm. If you don't include algorithm, it will not recognize your sort. It'll just say like, what is this? Like, this doesn't exist. I don't know what this is. But once you include algorithm, this function is included within that package. So whenever you're using sort, just always remember that you need to do hashtag include algorithm. Yeah. In both cases, sorting takes O of n log n time. This is basically something that you have to remember. So sorting takes O of n log n time, and yeah. There are many different sorting algorithms. Generally, most languages use quicksort, although C++ uses merge sort. It's very similar, but they have different pros and cons. Quicksort, the worst case could be n squared, but it's very unlikely. And merge sort is always n log n, but as a lower constant, as a higher constant factor. Yeah. Okay, so how would we use sorting to solve a problem? Well, let's say we have a problem that's asking us to find the number of distinct values in our array. How would we solve this with sorting? Well, what we can do is we can basically sort the entire array, and then once we've sorted the array, we can notice that all of the values that have the same value will always be next to each other in the array. So now we can basically just check how many indices are there where the number at that index is different from the number right before that index. And once we're able to calculate that, which is easily done with a simple for loop, we can find the answer. So this is like a very simple but illustrative way of how to use sorting to solve a problem. Yeah, does everyone understand that? Okay, I guess we can move on. So searching. So searching can be done with a lot of different things. Like, for example, we talked about complete search last time, but last time complete search, we know that it's very inefficient. You need to like go through every single thing, and that's not very good. Like, that's not efficient. So we can do it in a much more efficient way. And one of the more efficient ways that are very easy is binary search. So what is binary search? Well, you might notice that it's USACO silver level. So if you're just trying to pass bronze and don't care about like silver stuff, then you don't really need to listen. But it's very important, and it's also a very useful method of solving problems. So binary search is kind of like a method to find a certain value within a sorted array. Note that it has to be sorted. If it's not sorted, binary search will never work. The idea is basically to do the following. You basically like have a range, which is our search space. Our search space is kind of like all of the possible places where the answer could possibly be. And now we want to basically cut the search space in half. And by doing it, and if we're able to do this, then it'll only take us O of log n operations before the search space is cut down to a single point. And once it's a single point, we can easily find the answer. So we can use binary search for this. If we just check the midpoint, we can either tell that it's in the left half or the right half, because let's say the midpoint is less than the value that we're looking for. If the midpoint is less than the value that we're looking for, everything to the left is also going to be less than the midpoint. So this is M, everything here is less than M, and everything here is greater than M. So if our value is greater than the value at the midpoint, that means that nothing less than M could possibly work. So that means that we can just basically shift our attention only to our right side, and we would have the search space. Same thing if it's less. If our value is less than the value at M, then there's no point in searching for any values that are greater than M, because they will, of course, not be our answer. So we can reduce the search space down in half into the first half of the array. And once we're in the first half of the array, we can basically do that. Yeah. So that means in each operation, we'll reduce the search space down in half. And that allows us to have a time complexity of O of log n. Yeah, does that make sense to everyone? Don't be afraid to ask questions. Like, this is like by far the most complicated thing that we've done so far. So it's natural if there are questions about this. Okay. If there are no questions about this, we can talk about more applications of binary search. So there are more applications of binary search other than just searching through an array. Like this can be very useful, especially when you're stuck on problems and you're like thinking about how to like directly calculate the answer. Because in many cases, binary search works on anything that is monotonic, any function that is monotonic. For example, if you have a function that returns only zeros and ones, and it starts with a bunch of zeros, and then at one point it's a one, and then afterwards it's all ones, you can figure out that point where it switches just by using a binary search. And this property means that you can do a lot of really, really cool things with binary search. For example, you can binary search on the answer, which is a technique that is very common with problems that seem impossible. But then once you know binary searching on the answer, it becomes super, super easy. So yeah. So what does binary searching on the answer do? Sometimes it's very, very, very hard to directly calculate what the answer is, if not impossible. But you can easily tell, given an answer, whether it would work. And working is essentially like let's say you want to find the minimum value that satisfies a certain thing, and you can basically tell whether a value would work, but you don't know if it's the minimum value. Well, then you can do binary search really easily to solve this problem. And the way you can solve this problem is you basically need to find the search space, which is usually on from 0 to however big the answer could possibly be. And then after that, we can do binary search. We can basically get a bunch of values, check which one, if it works, then we go to the lower half. If it doesn't work, we go to the upper half, and then we keep doing that. And we'll get a really fast time of O of checking time, which is basically the amount of time it takes us to check whether an answer works, times log of the search space, which is the upper bound minus the lower bound. And this is often very good because sometimes the answer, it goes up to 10 to the 18. It seems like if we do a complete search, it won't work. But if we take the log of that search space, then we get something that's closer to like 30. And when we get something that's like 30 or like even 60, that's so much faster. And that allows us to have our program run really fast. Um, yeah. However, there is a caveat to this trick. And this trick only works if your answer is monotonic. What does that mean? Well, that means that if your answer only works, like if your answer works, that means that it works for everything that's bigger than it. And if your answer doesn't work, that means it doesn't work for anything that is lower than it. So it has to form like a bunch of zeros and then a bunch of ones. You can't have interleaving zeros and ones, or else this will never work. Um, yeah. Are there any questions about this? Again, this is like very hard, so it's very natural if you would have questions about this technique. Okay, I guess there are no questions. So, yeah. So let's do a practice problem. I didn't write the explanation, but here it is in the chat. Essentially, you are, if I recall correctly, you're given a bunch of cows and they arrive at a certain time interval. Let's say your cows are arriving at like times like this. Now you want to basically you basically want to minimize the waiting time of each cow, and the waiting time of each cow is essentially like, let's say you have a bus that can contain m cows. So let's say you have a bus, it contains m cows. I think yeah, but yeah, like a bus can contain up to m cows, and let's say this is your bus, right? That means that like from the start of the bus, which is this point, to the time of the last cow, this is your waiting time for this cow. And you want to minimize the maximum waiting time for each cow. And yeah. Yeah. Does anyone have any ideas about this problem? Like, I mean, there's okay. It seems people are very shy today. Hmm. I guess I'll give you guys until 4:30 to think about this problem, and then we can talk about it together, I guess. Oops. Anyway. Um, hmm. By the way, if anyone has any ideas about this problem, you can like send it to me in chat or something like that. Okay, so it's first need to say, well, if we keep like, let's say this is our, like, this is the first M, right? Or, uh, okay. Let's say this is the first M arrival times, right? Right? Okay, these are the first M arrival times, right? Let's say we have 2 buses. We, of course, don't want to take all of these. That would be completely suicidal, right? Because then our answer would be really, really big. But also, then how do we know what we take? Because if we like, if we have something like this and like this, like you know, it's like very hard to determine how many cows we actually want to take. It's just really hard to determine that. So if you think about this a little bit, you'll actually feel like it's actually impossible to directly calculate the solution. So how would we do this? Well, remember binary searching on the answer. Let's say we want to do that. How would we figure out whether a certain time would work? Um, yeah, I'll give you a couple more minutes to think about that. Okay, if you guys are still struggling with trying to determine whether something would work, well, think about it this way, right? Now you have two conditions as to when you would break. You have the condition of either um, it goes past, so let's say this is the amount of time you're allowed, and this is the number of cows you're allowed. So now you have two conditions, and you can just choose between which one. But are there any other choices? Are there any other choices besides those two conditions that you can make? Like, can you choose anything before like this? Like, would it ever be optimal to have something like this? Think about that. Okay. Well, if you're interested, there's actually no reason for us to not take this because, anyways, we don't care whether we want to decrease the answer even further. All we care about is that it's less, and as long as it's less, we don't care how much less it is. So we would always want to keep taking it until either the bus is full or until we can't take any more because of the time restriction. And now all we need to do now is basically do that for a bunch of different buses. Like you take the first one, you find how many you take, then you basically remove those, and then you do the next one, and then you find how many you take, you remove those, and then you keep doing that. If you keep doing that, then once you finish, you're just gonna be done. And then once you're done, like you can either figure out if you run out of buses and you still have cows left, then you know it's not possible. But if you still have cows, or if you still have buses, but you don't have any cows left, or you like don't have any cows left in general, then you know that it's going to be possible to do with that time. And so with that, you have a function of being able to check whether it works. Yeah. Yeah. Does that make sense to everyone? Oh yeah, also one final note is that if you want to binary search on the answer, you always have to consider that like you have to always like be aware that your thing has to be monotonic, but in this case that should be quite obvious, because if it's because it's obvious that if one time would work, increasing that time can never hurt your answer, so it'll always work if one time works. So yeah, this is a pretty neat way of using binary searching on your answer to be able to solve a problem. Yeah, that makes sense to everyone, right? Okay, I guess if there are no questions, then I can move on. Also, I recommend that like for all of the problems where I'm providing a link to the like practice thing, you should always try to like submit those problems, like even if they're not part of homework, you should try to submit it just to make sure that you like understand what I'm talking about, you understand the solution, and also you understand how to code the solution. So like this problem is a great problem to like try to like implement by yourself at home, even if it's not a homework problem. Yeah. Yeah, here, yeah. Okay. Now let's do recursion. So recursion is often a useful tool to solve many problems. You basically define a function outside of your main function. Basically, you can define the function type, like how to define a function. Well, it shouldn't be too hard. You define a function type. Well, okay, wait. So you function type. So you can define a function type either void, meaning void means it does nothing, int means it returns an int, and like other things like character, bool, you can do all of those. But let's say you have a void function and then you take in a bunch of parameters. So like, for example, you take in one integer and then let's see, like, it's defined by the brackets. And then in the middle, you can basically do something like basically do something. This is basically how you define a function. And the way you do recursion is also very simple. Recursion is essentially the act of like calling a function within itself. So if I say func return 1 plus func of x minus 1, this would be a recursive function. It would basically call itself over and over and over again until like, okay, let's say we have a corner case if x equals to 0, return 0, and then we do this. This would be a recursive function. So what happens is you go into the function, it calls itself again. So before it's able to like completely return itself, it will add another copy of itself to the stack with different parameters. And then it'll keep doing that until one of them returns. And then you can go all the way back through the function and then you'll be able to figure it out. So for example, in this case, let's say this is your function. We can like kind of like mimic the call stack here. So in the first call, the function will, let's say you call 5, right? So now you have func 5 on the stack. You have func 5 on the stack. Now it calls func 4, but before func 5 returns, it has to evaluate what func 4 is. So it'll put func 4 on the stack. And then to do that, it'll do func 3. And then it'll do func 2. And then it'll do func 1. And now, once it does func 0, notice how it returns. So now it returns 0. So now it backtracks through the stack. So it gets rid of the func 0, and then now it goes to func 1. And because it knows func 0 is 0, it basically makes func 1 equal to 1. And then after that, you can basically, we can get rid of func 1, and then equals 2, and then equals 3, and then equals 4. And then at the end, it finally evaluates this to be equal to 5. Oh wait, this shouldn't be void. Anyways, yeah, if that makes sense. Yeah, that's basically recursion. And sometimes like you might want to call a recursive function multiple times. And so if you call it the first time, it'll do the first thing, and then it'll like get rid of all the copies of the first thing from the stack. And by the time you're doing the second thing, it'll basically be like the stack will be empty, and then you'll be able to add to the stack from the second. Yeah. And like this act of like adding to the stack and removing from the stack can get really, really complicated at times. But if you keep it under control, it will work out, definitely. So I'll just give you an example. So one very common example problem is generating subsets. And to generate subsets, we can use recursion. For every element that you take, or for every element, you can either take it or you not take it. If you take it, then you can basically set that to 1 and then go to the next index. If you don't take it, you set that to 0 and you go to the next index. And so this is like a relatively simple function of being able to generate all the subsets. And this function actually uses like a very structured and a very like easy way to keep your recursion in control. So what do I mean by keep your recursion in control? Well, basically what you want to do is you basically want to first do your corner case. So first, or not corner case, but like base case. So first you want to handle a base case. So handle base case. Okay, so first you want to handle the base case. And once you handle the base case, that makes sure that you won't have like infinite loops and stuff like that. Once you handle the base case, you go down to the actual recursion part of the thing. So for each recursion, you can do a for loop for this as well, but for each recursion, you want to basically do, set variables, or you do like a for loop for each like for each thing. For each thing, you basically want to generate the next one, right? But before you generate the next one, you must like set some certain values and then generate the next one. So what you want to do is you want to generate the so you set the values, actually I think this will be better if we did it in text. So basically here, the idea is for each recursion, you basically want to set each value, set required values, recurse, and then reset required values. And the reason this works is because or the reason you have to do all of these steps is because when you're setting the required values, you're essentially like basically unique, making all of your recursions unique. And then when you recurse, you're basically actually doing the recursion. And then the last step is the one that most people forget, but it's also something that causes a lot of bugs. And you have to reset all of your required values, because if you don't reset your required values, you'll eventually have everything set to the last thing. And once you have everything set to the last thing, like you won't get anything from recursing, and it'll just like output the same thing every single time. So you have to reset all of the required values before you even do any of the recursion stuff. So or not before, like, but it's like one of the most one of the most important steps that is often overlooked. Like that, and if you're using recursion, that could be the biggest source of all of your bugs. So you should watch out for that. Yeah. Make sure you reset all of your required values. But yeah. Does that make sense to everyone? Okay, if that makes sense to everyone, then let's keep going. So yeah, complete search with recursion. Sometimes you'll need to use recursion to do your complete search. For example, if you needed to find a certain value over all subsets, then the easiest way to do that is to use the recursion, generate the subset, and then after you've generated the subset, when you're checking the base case, instead of outputting it, you can basically check whether it is working or like check whether it is optimal and like update your thing. So that's one way. Another thing is like another common way that it occurs is if you need to like check based on all permutations. Permutations are very similar with recursion. You can do permutations essentially the same way with recursion, and yeah, you can again do like the same structure of your code, and then at the start when you're handling the base case, instead of just like outputting the permutation or something like that, you can just like find whether it's optimal. Yeah. Does that make sense to everyone? Okay, if it makes sense to everyone, then I guess we can do the challenge problems now. So there's the 3 challenge problems. There are actually 4 challenge problems. The last one is to try to write binary search in 2 different ways. So binary search can either be written recursive or iteratively. And you can like check them against each other to make sure that they're correct. But yeah, try to write both of them, and then yeah. This won't be a problem on Codeforces because Codeforces will not be able to check whether you're using recursion or you're using iteration. But you should try to do both of them because both of them have their merits, and yeah. Yeah. The rest of these problems can probably be found on Codeforces, although let's see if Codeforces is still down. Oh, Codeforces is still down. Okay. Oh well. Okay, I guess I'll explain these problems. So the first challenge problem is sorting. You have an array and you want to basically split it into 2 sets, A and B. And you basically want the size of A to be bigger than this, or to be less than the size of B, but the sum of all elements in A is greater than the sum of all elements in B. And you want to output whether that is possible. So that's problem A. Okay, problem B is binary search. So for Q queries, you want to basically calculate the minimum number of elements that you need to take in order to have a total sum of at least X. Basically, let's say you have an array of like 1, 2, 4, 3, 10, 7. You basically want to find the number of actually 0. Okay, you basically want to find the minimum number of elements you need to take in order to have a total sum of at least X. So let's say X equals to 11. Then you just need 2 elements. Let's say it's 7 and 4. You just need those 2 elements in order to have a sum of at least X. Yeah. And you have Q of those queries. So yeah. Yeah. And the last problem is you have n ranges and you're given the start time of each range. This is actually very complicated to like explain, but essentially the idea is that let's say you need the total sum of like all of the ranges that are covered to be H. So you need the total amount of cover for all of your ranges to be at least H, right? And you are given that at the start, everything has length or everything has length equal to K. And if something is covered twice, it only counts once. So like, for example, here, let's say this is 1, 2, 3, 4, 6, 8. Like, let's say everything has length 2. And if you count the total cover of this, it's like 5. So it takes like, so the total cover is 5. But let's say you wanted to make the total cover like 10. Then you need to extend K even larger. And at some point when you're extending K, it will eventually be able to be at least the X. So yeah, that's kind of the problem. It's kind of hard to explain, but yeah. Yeah, and the last problem is to try to like implement binary search yourself 2 ways. So both recursively and iteratively. Yeah, and it is very unfortunate that Codeforces still does not work. Okay, Codeforces still doesn't work. Yeah, I don't know why Codeforces has been acting up today, but yeah, as soon as it stops acting up, I guess yeah. Okay, I guess in the meantime, do you guys have anything that you would want to go over? Actually, never mind. Wait, actually, I have all the 3 problems here. So, yeah. But like, I guess I could send the link as well, but like Codeforces won't work. Like if I reload this or click anything, it won't work. So yeah. Are there any questions about the material? I'm fine with like going over anything. I don't think USACO is down, so yeah, USACO is definitely not down. So you can check, like, I think the problem was here. Yeah, you can check this problem and try to submit this one, I guess, in the meantime. But yeah. Okay, so I guess Codeforces will just not work. So I guess we could end it here. Especially since there aren't any questions that people are gonna ask me. So yeah, we can just end it here, I guess.